Right, ladies and gentlemen, let's continue with chapter 11. In chapter 11 is about heat exchangers. We've started with an introductory part on the different types of heat exchangers. Then we've looked at the LMTD method, and then Dr. Marlies Everts did the effectiveness-NTU method with you, which was in paragraph 11.5. And that is where I want to continue today. It is just a small part of the work, but in general it is therefore chapter 11.5, the effectiveness-NTU method, and I would like to continue with that work that Marlies did. And specifically under table 11.4, there are some observations that can be made about the effectiveness-NTU method, and there are 4 of them listed underneath table 11.4. The 4th one is the one that I would like to say something about, and that is sort of fine print in the textbook, but specifically in this method is most probably the most important part. It's a small thing, but if you do not pick that up, then unfortunately in the exam, then most probably you will not do the problem correctly. So in point 4, they say that there are cases where C, which is of course C minimum divided by C maximum, is equal to 0. When will that be equal to 0? Well, it will be equal to 0 when C max is going to infinite, or when it is very large. Now, when is C max going to infinite? C max is very, very large in the cases where we have condensation or evaporation. Evaporation or boiling. And for those cases, if you've got the case where C equal to 0, then the effectiveness of your heat exchanger is equal to E max is equal to 1 minus E to the minus NTUs. NTUs, the number of transfer units. So that is a very important equation that is valid if we've got condensation, boiling, and or evaporation. When do we have condensation, boiling, and evaporation? What does it mean? If you go back to your thermodynamics, to TS diagram, that is the saturation curve. And then for a specific pressure, so that is the line where the pressure is equal to constant, condensation, remember, that is where everything is a gas, that is where everything is a liquid. So this will be, condensation will be the case where the gas changes to a fluid, or boiling or evaporation will be when it changes from a fluid to a gas. It therefore means that in general, it is always when we've got a two-phase change in the working fluid. And that happens a lot, typically in air conditioning and refrigeration systems, and as well as in a Rankine cycle. We've got the 2 pressure lines, like that. In a vapor compression system, we will have a compressor that would compress the fluid from 1 to 2. Then there will be a little bit of superheat and it will condense. So then it is condenses. We will do a little bit of where we undercool the fluid. It will expand through the expansion valve, and then it will be boiled again. So that's the boiling. So that is the direction of the cycle. So that is a vapor compression cycle. Rankine cycle is in principle exactly the same. Our TS, there's our two pressure lines. Here we will have a pump. Not like that, because the entropy will always increase from 1 to 2. That is our pump. Then it is being pumped to the boiler. In the case of fossil fuels, a big boiler, a fire that is being made, it will boil the water so that everything is superheated. Then it will be expanded through the turbine there, produce work, and then it will go to the condenser again. So there's the condenser, there's the boiler, and that would then be our Rankine cycle. Take note that this, of course, as we've mentioned previously, is the G point, and that is the F point. And the difference between the two for the enthalpy values, that difference there is HFG. HFG. And although, as you can see, in most cases, we've got a superheat there, it is undercooled there. If you go and look at the change in enthalpy from there to there and from there to there, those parts would normally be negligible in comparison with the two-phase change enthalpy values. Also, looking at this thing very critically, the effectiveness is equal to 1 minus e to the minus NTUs. When we looked at internal forced convection, I discussed with you how important this NTU is, the number of transfer units. It is equal to the overall heat transfer coefficient multiplied by the surface area divided by the mass flow rate and the CP. And I've indicated to you that if NTU is 5 and larger, then it's not a good design, because at 5 you're going to approach the other temperature, and you'll see what I mean with that in terms of the example that we're going to do. But let's go and look typically at different values of NTU. And you calculate the effectiveness is 1 minus e to the minus NTU. What will the effectiveness be? So if the number of transfer units is equal to 5, and you calculate 1 minus e to the minus 5, then the effectiveness would be 0.99999. If it is equal to 4, 1 minus e to the minus 4, then it is 0.98, 98% efficient. If it is 3, 1 minus e to the minus 3, then it is 95% efficient. Well, to make it clearer, let's look at an example. And the example I'm going to look at is problem 11.116 in your textbook. And this problem says the following. I'm going to read it to you first, and then I'm going to show it on the board. Steam is to be condensed on the shell side of a 1 shell pass and 8 tube passes condenser with 50 tubes in each pass at 30 degrees Celsius. HFG is 2431 kilojoules per kilogram. Cooling water, CP4180, enters the tubes at 15 degrees at a rate of 1,800 kilograms per hour. The tubes are thin-walled and have a diameter of 1.5 centimeters and length of 2 meters per pass. If the overall heat transfer coefficient is 3,000 watts per square meter degrees Celsius, determine the rate of heat transfer and the rate of condensation of the steam, and then I'm going to put another part to it and say redesign the heat exchanger to make it better. Now, what is better, we will get to just now. So schematically, I'm going to show this condenser like this. This is the shell. And we are going to have the steam at 30 degrees Celsius entering there. And here we're going to have the water, and the water is going to enter at 15 degrees Celsius. It's water, and its mass flow rate is 1,800 kilograms per hour. Its CP value is given for us as 4180 joules per kilogram Kelvin. HFG is equal to 2431 kilojoules per kilogram. The overall heat transfer coefficient of the heat exchanger is 3000 watts per square meter degree Celsius. It has 8 tube passes. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, and going out. Okay, so this blue is the colder side. So we are using the water to condense the steam. Okay. So in terms of a TS diagram, this is the steam. Okay. And take note, this is now an important thing. If they tell us it is condensing at 30 degrees Celsius, the condensing temperature is that temperature there. Condensation would mean we've got a phase change from a gas to a fluid. Okay, so that HFG is equal to 2431 kilojoules per kilogram. Are you all with me? Okay. Okay. So it's very important to realize if we've got steam, it's condensing, the temperature remains constant. It means that although the outlet temperature is not given, it is logical that the outlet temperature should be 30 also. So if we show it schematically, then if that was the inlet temperature, then the outlet temperature of the steam remains constant if there's no pressure drop. If there's a little bit of a pressure drop, then of course that would not be the case, but that you can take into consideration in more sophisticated calculations. The water that enters at 15 degrees Celsius. We don't have the outlet water temperature. Now, look at this problem and try to figure out how are we going to start this problem. We've got from the steam, we've got its temperature and we've got HFG. So if we had the mass flow rate of the steam, it would be possible for us to determine the number of kilowatts, but we don't know that. On the water side, we know the temperature and the mass flow rate, but we don't have the outlet temperature. So we don't have the heat transfer rate for any one of the two streams. So that is why the effectiveness-NTU method is now such an effective method. And taking into consideration that when we've got condensation or boiling of evaporation, then the effectiveness of the heat exchanger would be equal to that. So let's just schematically show a typical temperature. Well, it doesn't have to be linear. Let me rather not do it like that. Let's rather do it something like that to show it's not linear. So this is the water side, T water. That is the inlet of the water, that is the outlet, and that is the temperature of the steam, and that would be the inlet and the outlet. Now C minimum, or one of the C's, would be equal to the mass flow rate multiplied by the Cp, and it should be on the cold side. And we are going to use the water side for that. Why? Because of this. If we've got condensation or evaporation, it means that C, the ratio, C minimum divided by C maximum is 0. Why? Because C maximum is infinite. Okay? There is no, if you go and look at C, which is equal to the mass flow rate multiplied by Cp, there is no Cp value during two-phase fluid. Okay. There's a Cp value if it is only a gas, there's a Cp value when it's only a fluid, but during phase change, Cp value doesn't exist. So by implication, the Cmax would always be the phase change process. And therefore it implies that always C minimum is the other stream in which there's no phase change. So the mass flow rate of the water is 1800 divided by 3600, because it's 1800 kilograms per hour. The Cp value they were so kind to give to us is 4180. So that is equal to 2090 watts per degree Celsius. Then, noticing this observation that was written here in terms of C max minimum divided by C maximum, we can now do the same. We can say C is equal to 0 because it is equal to C minimum divided by C maximum, because C maximum is infinite, and therefore it has been derived previously for the effectiveness-NTU method. Qmax is equal to C minimum multiplied by, okay, now you have to look here very carefully now. Cmax is the maximum possible heat transfer that the heat exchanger can give you. Okay. What will that be? If the inlet temperature is 15, the maximum will be if this outlet temperature is 30. You agree? Therefore, it should be something like this. That would give us the path for Qmax. Remember, that outlet temperature can never be more than 30. It can only change from 15 to 30. That is the best you can do. Okay. Therefore, it would be equal to let's call it T of the steam inlet minus the temperature of the water in. So C minimum is 2090. That temperature is 30 minus 15, the maximum possible temperature difference that heat exchanger can give you, and that would be equal to 31.35 kilowatts. Okay, so now we know what is the maximum possible capacity that heat exchanger can have, just because of the inlet temperature and the condensing temperature. Those are the two thermodynamic limits that we have. The routine calculation that we're going to use is the surface temperature of, it is 8 tube passes. So 8 of them, 1, 2, 3, 4, 5, 6, 8. And what they say is that every one of these tube passes have 50 tubes. So there are 50 tubes passing through this thing 8 times. And every length here is 2 meters, 2000 millimeters. So it is 8 tube passes multiplied by 50 tubes multiplied by the diameter, which is 15 millimeters, multiplied by the length, which is 2 meters, and the surface area of this heat exchanger is thus equal to 37.7 square meters. 37 square meters. Okay? Now, in terms of the NTUs, the number of transfer units is equal to the overall heat transfer coefficient multiplied by the surface area divided by C minimum. That's been defined with the previous lecture. The overall heat transfer coefficient is 3000. The surface area is 37.7. And C minimum is 2090. And that would give us a value of 54.11. 54.11. Now, if you've done some heat exchanger design, you should frown here. For 2 reasons. Firstly, maybe you've made a calculation error, so you need to go and check this. But coming back to what I've already warned you on in the chapter on internal forced convection, if your NTUs is more than 5, you're wasting money, because your effectiveness will already be 100% for all practical purposes. So in general, never go more than 5. Even 3, as you can see already, is sort of the upper limit. What is also important to see is, if you look at the graphs of the effectiveness as a function of the number of transfer units for a tube-in-tube heat exchanger and all the different heat exchangers. Very difficult to see them properly, but in general, all of them have 2 things in common. There's the effectiveness and there's the NTU. For all those graphs, they do something like that. And this one, which will give you the highest value, is C equal to 0. You see that? And then underneath it, it would be C equal to 0.8, 0.6, etc. So that is the highest one, where C is equal to 0. And you will see at approximately 3 to 5, all those gradients are approximately constant. Okay, so frown on it, but we will come back to it. 54.1. So if we now calculate the effectiveness, which is equal to 1 minus E to the minus NTUs, is equal to 1 minus E to the minus 54.11. and the result is equal to 1. Effectiveness is 1. Thus, if that is so, then the total heat transfer rate would be equal to the effectiveness multiplied by Qmax. The effectiveness is 1. Qmax we've already calculated is 31.35 kilowatts. So in this case, we will get the maximum possible heat transfer rate is 31.35 kilowatts. We would still like to do two things, and that is we would like to calculate the mass flow rate of the steam, and we would like to calculate the outlet temperature. So let's go and do that quickly. The heat transfer rate would be equal to the mass flow rate, the mass flow rate of the steam multiplied by HFG of the steam. The heat transfer rate is equal to 33.35 kilowatts. The mass flow rate of the steam is what we want to calculate. The HFG value is equal to 2431. Take note, it is kilojoules, so it is multiplied by 10 to the 3, and then we can calculate the mass flow rate of the steam, and that would be equal to 0.129 kilograms per second. It's not an engineering answer, but you can multiply it by 3,600 to get it in kilograms per hour. But there's the value. And then lastly, let's go and check the outlet temperature of the water. The heat transfer rate of the water would be m dot Cp, and then it would be the water outlet temperature minus the water inlet temperature. We've got the heat transfer rate is 31.35 multiplied by 10 to the 3 is equal to, the mass flow rate is 1,800 divided by 3,600. The outlet temperature is what we would like to get. Inlet temperature is 15 of the water that is being used to do the condensation, and therefore, guess what? The outlet temperature of the water is 30 degrees. Okay. Therefore, in terms of what can happen, in terms of T and X, let me just get my color. The hot water is going to condense. It's going to remain at 30 degrees Celsius. The inlet water is going to come in at 15 degrees, and its outlet temperature is going to be exactly 30, because the effectiveness is 100%. Okay? So that might be great, but redesign it. Redesign it, coming back to this massive value of 54.11, and what I've showed you, if the NTUs is equal to 5, you're going to get an effectiveness of 1 again in any case. So what would be the first thing that we're going to do? We're going to say, in terms of the redesign, at least the minimum, we're going to say, let's change the surface area and make it 10 times smaller. That's we're going to make it not, what was it, 37.7, we will make it 3.77 square meters. So it's 10 times less. How can we do that? Well, in terms of this number of tubes, 50 of them, we can make it 5. Okay, just to start with. So let's make n equal to 5. And then you can go through exactly the same calculations, and you're still going to get the NTUs, is then of course going to be 5.4 for 1. The effectiveness again is going to be 1. Your heat transfer rate is still going to be 31.35 kilowatts. So exactly the same heat transfer rate, exactly for the water. Outlet temperature is still going to be 30 degrees Celsius, but you use 10 times less surface area. Okay. So if I would design this, I would definitely not go to 5. I would definitely go to 3 and less. Okay. Does that make sense? Any questions? No questions? Carl, thanks.